Good evening, everybody. Thanks for coming. We're going to hear about imaging of the heart from Professor Williams in a little bit. Just to introduce Michelle, a few things. She studied medicine at Edinburgh. She managed to squeeze in an OU degree in maths and history at the same time.
During my PhD.
Did a PhD on computed tomography, which is CT scanning to you and I. Yeah. So in that, moving towards that kind of field, and did her history and maths as a wee bit of a hobby, by the sound of it. But she was telling me that she was, I won't give you secrets away, was scanning mummies or CT and looking at disease and all sorts of things. Tremendous stuff. So Michelle's in that kind of field of using computer imaging to investigate, in this case, coronary heart disease. She's a consultant radiologist with NHS Lothian and is associated with the University of Edinburgh too. She has a research team working with her in all sorts of disciplines. She is also an associate director of the British Heart Foundation, which is very supportive as far as funding, etc. is concerned. So good on them, and keep buying your second-hand furniture. And is also part of the Scott Heart Study, and has over 260 research outputs. So Professor Williams is a busy and very capable lady. I'm really looking forward to this one. Close to my heart, this one is. Okay.
So, thank you so much for having me here this evening and for letting me talk about basically my favourite subjects. So, we went for dinner earlier, we chatted about these things already. I could talk about these things all night, and I hope you're going to enjoy them too. I'm going to talk about what I'm fortunate enough to get to do all day, every day, and that's looking at the heart. The heart is the most amazing organ in the body. A lot of people say the brain is really interesting, but I think it's the heart. And also how we use computers to look at the heart in more detail, and ever more increasing detail as the research progresses. So, as already been said, I'm Professor of Cardiovascular Imaging at the University of Edinburgh. I'm Associate Director of the British Heart Foundation Data Science Centre, and I have lots of other titles, but those are the main ones that are of interest this evening. I'm going to talk a bit about the potential of artificial intelligence, particularly in medicine and particularly in medical imaging, which is what I do. I'm going to talk about how this has made it possible to look at the heart using our imaging scans and tests in all new and different ways, really the state of the art in cardiac imaging. And I'm going to talk about some of the challenges of this, because I don't think we can talk about artificial intelligence without also talking about the challenges that comes along. But let's start at the beginning. What is artificial intelligence? There are many different definitions for this. One of the problems is there isn't really an official definition of what artificial intelligence is. Everyone has their own idea as to what it might be. My favourite definition is this one: intelligence demonstrated by machines. Nice and simple, and kind of encompasses most of the things that we're going to talk about. And there's different types of artificial intelligence. There's artificial narrow intelligence that just does one thing. There's artificial general intelligence that does many things like a human would do. And then there's artificial superintelligence, and that's where the sci-fi books kick in, and the movies, the Terminator, things like that. Fortunately, we do not have artificial superintelligence. We also don't have artificial general intelligence. And actually, we don't even have artificial narrow intelligence at the moment, because all of this requires intelligence demonstrated by a machine. I work with computers all day, every day. There are some amazing programs that I use all day, every day. These are very, very clever things, possibly cleverer than I am, but they're not intelligent. And that's the one thing that separates us from the computers at the moment, and possibly for this foreseeable future. So what we're actually doing is a subset of this. We're doing machine learning. We're using computers to do tasks. Very complicated tasks, but still computers doing tasks. Sadly, no intelligence yet. My husband is a computer programmer, and he has what I think is one of my favorite definitions of what artificial intelligence is. And he says, if you're not mortally afraid of its potential ramifications, it's not artificial intelligence. So today I'm going to be talking about machine learning. The marketing hype will tell us that it's artificial intelligence that's in our cars and in our banking systems, but it's actually machine learning. And so even as someone who knows all of this, I keep slipping into calling it AI and artificial intelligence, but I'm actually meaning machine learning. There's lots of different types of machine learning, and every time I read up on the latest papers in this area, someone's invented a new type of machine learning. But they sort of split down into three general groups at the moment. The first is supervised intelligence. And that is training machines to do specific tasks. So red dots versus blue dots, or blue dots along a line. These are all types of supervised machine learning. There's also unsupervised machine learning. And this involves giving the computer lots of information and seeing what it finds. Not telling it the answer, just letting it have a shot, see what patterns it finds amongst the data. And I really enjoy doing this type of machine learning because it takes away our human biases and actually tries to help us uncover what's under the hood within the data itself, rather than just being guided by humans. So I do a lot of unsupervised machine learning. And actually, there's lots of combinations in between. One of the types, the third type of machine learning that you might have heard about in the past is reinforcement learning. And this is where we give machines their equivalent of sweeties if they get the answer right, and a slap on the wrist if they get it wrong. And this is actually what was used to train Deep Blue and some of the early 90s systems that bet Kasparov at chess. So that was reinforcement learning. So our package of work that we're doing at the moment kind of involves all of these different types of machine learning and many more. And actually, machine learning is all around us, often without us really knowing. It's in my car, it's showing what news I'm going to see when I log into social media or news apps. It's in the background in our financial system. It's the thing that does the pinging up of those messages saying, do you really want to pay this money, the texts that come in from the bank? It's in the background a lot of the time. Sometimes it's more in the foreground, but a lot of the machine learning that we're exposed to in our daily lives is actually in the background. And we've been talking about this for quite a while. Back in the 1950s, Alan Turing wrote his seminal paper on this. And there was a slow development of ideas from then. The words artificial intelligence were first discussed at the Dartmouth conference in 1956. And then the first ever chatbot actually came along in 1965. So these things are not new. We've had them for a while. They've just been a bit slow to get started. And there've been a variety of what's been called AI winters, when the technology's just stagnated and not really developed. The first AI winter was because we really didn't have computers that were capable of doing the things that we're talking about. A lot of this early work in the 50s and 60s was written out by hand. In the 80s and into the early 90s, we had the second rise of machine learning, and this was when computers were really starting to develop. And these were a lot of expert systems that were developing. The World Wide Web came along in 1989. Deep Blue beat Kasparov at chess in 1997. And this was another really exciting time in this AI and machine learning world. But we had a second AI winter, and that one was partly because we didn't have enough computers and enough memory, but also we didn't really have data sets. Fundamental to all of this development of machine learning is the data that underlies it. And in the 80s and 90s, we were just developing memory sticks that were big enough to hold 10 or 20 songs, let alone thousands of data points from machine learning tools. So there was a second AI winter as things stagnated around then. But since the early to mid 2000s onwards, there's been a constant rise of how we use these things and developments. Deep learning came along in 2006, and I'm going to talk a bit about that later on with some heart examples. IBM Watson won at Jeopardy in 2011, and one of the big successes was AlphaGo beating the world champion Go player. I don't know if any of you have tried playing Go. It's really difficult, so a machine learning that was particularly good from a technical point of view. But in the past few years, there's been a huge explosion, and it started in 2021 with large language models, with ChatGPT. So can I have hands up in the room who's used ChatGPT or Copilot or any of these large language models? So many people have used it, have a shot of it. It's great fun. It can do so many different things, and I'm going to talk a bit about what it can do in a medical sense a little bit later on. It also can come up with total rubbish. As you will know from having tried it out. It's very good at planning holidays. I've found it's great for planning routes around new cities, but I won't trust it with any medical questions for the foreseeable future. The big question is what's coming next, and we could be seeing at the start of an exponential rise. It's just going to go up and better from here. Or this could just become business as usual. Is this just going to be the new calculator app on your phone, the new spreadsheet, the new tool we always use? Or are we heading for another AI winter? And we've got to be very careful that the hype of all of this doesn't exceed its abilities. And the marketing hype around artificial intelligence doesn't worry me a little, because we do have to be realistic about what it can and what it can't do. So I don't know what's going to happen, can't predict the future. I suspect business as usual might be the way it's going, but we'll find out over the next few years. So that's my introduction to what AI is. The question is, well, what can it do in healthcare, both now and in the future? And because I'm trying to predict the future here, there is definitely a word of warning. I have given many lectures over the past 10 or 15 years. Some have proven to be totally correct, and others not at all. And that's one of the things with machine learning. We just don't know exactly what's going to happen. But I always look to this guy when I'm talking about this stuff. There's no harm in trying to predict the future. But this is what Thomas Watson, the president of IBM, said. 1943, I think there's a world market for maybe 5 computers. Well, I've got 2 in my person, a phone, a number of computers. There's 5 within a meter of me. So he got that one wrong, but he got many other things right. So let's start talking about the heart, which is one of the really interesting things that I get to spend all my day looking at. The heart is an absolutely incredible organ. It beats 2.5 billion times in your lifetime, and it never gets a day off, not a single one. Every single day, every single minute of every single day. And it's an incredible organ. The brain just does one thing. It processes brainwaves. The heart is a combination of stuff. It's a pump. It's actually the most incredible pump that's ever existed. From an engineering point of view, we've tried to replicate this pump, and we can make very good artificial hearts now, but they're not as good as the heart itself. It also has valves. The control system of the valves in the heart is very precise. It has an electronic control system, so there's actually a brain in your heart. There's actually 2 little brains in your heart that are connected together. So it clearly beats the brain. And it also contains millions of tiny little blood vessels. So my research spans across all these aspects of the heart. But the thing I'm most interested in is the blood vessels that supply the heart, because that's where you get coronary heart disease of the heart blood vessels. Heart disease is an incredibly important condition. It touches all of our lives. 7.6 million people in the UK are living with heart and circulatory disease. around 1 in 3 people in the world will die because of heart and circulatory disease. Every 3 minutes, someone dies from heart or circulatory disease in the UK. Every 3 minutes. And 13 babies with congenital heart disease are born every day. Now, we've made great sway in improving all of these statistics over the past 50 to 100 years, but we've got a long way to go. And I'm incredibly grateful for the British Heart Foundation, who do 2 amazing things. The first is they support all of this research that we do, and many others do across the UK. And the second is that they support patients in most fantastic ways. So I would be remiss in my job giving a talk today if I didn't mention about what we can do to keep our hearts healthy. There are things that we can all do every single day. They can be tiny little things. They don't have to be big dramatic things like running marathons. Every tiny little thing that you do can help to keep your heart healthy. So climbing the stairs, eating an apple at lunchtime, not smoking. If you want to know more about how to keep your heart healthy, check out the BHF website. It's a fantastic resource of everything that you want to know about your heart. And if you do have questions about your heart, don't use ChatGPT. Use the British Heart Foundation website or go into one of the British Heart Foundation shops. I'm very grateful to the British Heart Foundation because they funded my research throughout my entire career, from my first ever scholarship all the way up to 2 days ago where I got my most recent fellowship. So it's thanks to them that any of the stuff I'm talking about today is possible. So if you shop in a British Heart Foundation shop or donate to the British Heart Foundation, thank you. So I'm going to talk about imaging tests. Now, there are lots of different types of imaging tests. They range from really simple ones, like chest x-rays. So the image at the top left is a chest x-ray of a very large heart, all the way through to really complicated scans. So next to the chest x-ray, we have echo. So the one in the top in the middle, this is an echocardiogram. This uses sound waves to build up an image of the heart. So pregnant ladies now get ultrasound scans to look at babies at various stages throughout the pregnancy. We can also use exactly the same technology to look at the heart, look at its shape, its size, and how it moves. At the bottom left is a CT scan. My research mostly centers on CT scans, so you're going to be seeing a lot more of those. Those use X-rays to build up a 3-dimensional picture of the body. And we can scan a little bit of the body, or we can scan the whole body. A lot of my research involves how we can get better pictures of the heart with a CT scan, because the problem is the heart never stops moving. So I'm trying to get a still picture of the heart, and that can be technically quite challenging. So we have some very fancy scanners in the various hospitals around Scotland that are capable of taking very, very fast images so that we can get the heart at a single time point. In the middle, we've got invasive coronary angiogram, and this is again an X-ray based test. But this one involves putting a wire in the blood vessel in the wrist or the groin, feeding it up towards the heart and injecting dye into those blood vessels so that we can see them, but also so that we can treat heart disease, maybe with a stent or with other treatments that they have that can actually treat the heart disease in situ. So a combination of an imaging test and a treatment in one, which is quite an exciting place to be. And then the last 2 images are some of the state-of-the-art images with our very fancy scanners. The one at the bottom on the right is an MRI scan. So that is using magnets to build up a picture of the body, actually developed in Aberdeen, so yet another thing that Scotland can be very proud of. And the multicoloured crazy one at the top is a positron emission tomography scanner. So it uses radioisotopes that we inject that go around the body and identify places where they're taken up, so we can actually study biological processes. Across all of these different imaging tests, we can do a few different things. One is we can see the size and the shape of the heart. Another is that we can see how it moves and how it changes over time. Is it going too fast? Is it going too slow? Is it pumping enough blood? Is it pumping too little blood? And then the third thing we can do is see how the heart is controlled and look at the valves and look at the electrical system of the heart. So these simple imaging tests that we do all day, every day in the hospitals throughout Scotland can tell us huge amounts of information about the heart and the heart blood vessels. Now, this is the only video I have, oh, and it works. So I was joking earlier, I never put videos in talks because you never know if they're going to work, but I'm very glad this is working. This is a CT scan of the heart. So this is a CT scan of a patient who participated in one of our research studies. And we don't use these images for diagnosis. These 3D images, however, can be really good to help explain what we're looking at. In this case, we've started with a zoomed out heart, and we've zoomed right in to this area of heart disease that this patient has. So this is the zoomed out heart of this patient, and we can zoom in on that individual blood vessel, and we can pretend that we're a blood cell going around the body. We're now inside the blood vessel, and those white bits are the coronary artery disease, the build-up of plaque, of fat, and of calcification within the heart blood vessel, and it narrows the blood vessel, so you can see that blood cell struggling to get through that blood vessel. And this is what happens in some forms of heart disease. So you can hopefully get an idea of the detail that we can see. We're not just talking about, is there a heart? Where is the heart and how big is it? We're talking about really small details that we can now see with these types of scans. But that causes us problems. There is a lot of information on a CT scan. So on the right-hand side here, you'll see a CT scan in the way that I normally look at CT scans. Grayscale, black and white, going up and down through the body. This is what I spend all day, every day looking at in both my clinical practice as a radiologist, diagnosing different types of heart disease, and also in my research. This is a scan that has lots of information on it. There are 3 or 4 diseases that I can clearly see, and my report would explain about all of them. But there are actually over 1 billion pixels just in the images I'm showing you there, and it's only a small bit of the chest. It has multiple organs, there's multiple diseases in there, and most of that information is never actually used. For the diagnosis, for writing the clinical report for this scan, I'll talk about all the things that we can see, but there's lots of information hidden in the fat and in the bones and in the muscles. And the more we look at this, the more we realize that actually this is very important for patients' health. We can't just think about the heart on its own, we have to think about the heart in the person as a whole. So the first challenge I have is there's a lot of stuff for me to look at. The second challenge I have is that the amount of stuff for me to look at is increasing really rapidly. This is some work looking at how imaging test use is changing over time between 2012 and 2019. Now, some types of tests are staying the same, some are decreasing slightly. Unfortunately, they are the easy and inexpensive ones. The red line that's increasing very rapidly is the CT scans. The reason it's increasing rapidly is we now know how useful it is. And as was mentioned earlier, one of the studies I lead in Edinburgh is called the Scott Heart Trial. Scott Heart's a large multi-centre randomised controlled trial looking at the use of CT scans of the heart in patients who have some chest pain. We showed 10 years ago that this scan was very useful, and that's why that line increases so rapidly. And we've been following up the patients who participated in this study ever since. And it was patients across Scotland, so there may be some people in the room who participated. So if you've participated in some of the research studies over the years, thank you again, because we really do appreciate the help that all of the patients and the public give us in actually making these research studies possible. So, what is the potential for artificial intelligence? Can it help me? When I think about artificial intelligence, in any discipline, in any way I'm using it, I kind of think of it in 5 different ways. And this is relevant for heart disease, but it's also relevant for other areas in medicine, and it's actually relevant for anything that we use artificial intelligence or machine learning for. So I'm going to go through these 5 different ways that artificial intelligence might help us. And I'm going to give you examples from my world, from cardiovascular imaging research, to show you what might be possible. But do think about how these might impact and reflect other things that you see going on as well. in healthcare or just in life in general. The first thing that AI can do for us is helping us do the things that we do every day just a bit faster and a bit better. Now, this is another CT scan of the heart, a still one this time. This shows the 4 pumping chambers of the heart. We've got 2 atria, which are the smaller chambers, and 2 ventricles, which are the bigger chambers. And the thickest one in the middle there is the left ventricle, the big pumping chamber that gets the blood out of your heart and around the body. Now, my PhD was assessing that big pumping chamber. And to do that, I had to draw around it. And because this was before we had artificial intelligence and machine learning coming along, I had to do that manually. So my PhD involved drawing 80,000 circles. Fortunately, we don't have to do that anymore. And I made a machine learning model a few months ago that can replicate my PhD, those 80,000 circles. I made it over the course of the weekend and it processed all the scans in a day. So that is much faster. So to me, that is a fantastic thing because we can do research and we can do things for patients much quicker. Not having to wait for someone to draw circles, we can get the research done faster. So I am very keen on anything that firstly avoids me ever having to draw another circle, and secondly, gets the research done quicker. We used to do research on 5-yearly cycles, that we'd make a plan, we'd then do it over 5 years, and then we'd think again and make the next plan. That cycle is reducing and reducing and reducing, and now I'm thinking of new research ideas every 6 months because new things are coming along. And to me, that's really exciting because that's where we're going to make a difference. The other thing is, can AI do it better? I don't think AI will ever be better than humans because it's only ever learning from what we do and replicating what we do. So it never has the innovation and it's never going to take the next step. It's only doing the things we've already done. The thing that it does do is it does things exactly the same, again and again and again and again and again. Whereas if I'm drawing circles, I know I can draw 20 and then I need a coffee break. My circles towards the end of that 20 are probably getting less accurate. So that's one of the things that AI can do. It can give us consistency as well. And when it comes to things like heart disease research, that's very important. So for me, it's really that gift of time. For me, it's one of the most important things that it gives me, that ability to do more things faster and more consistent. The second thing is helping us to do things that we want to do, but it's just not possible. And for me, that's analysis of those tiny little plaques in the blood vessels of the heart. So this is another CT scan, but shown in a slightly different way. The beauty of CT scans is it's a 3-dimensional data set, so you can cut it and look at it in all sorts of different ways, and you can also make 3D reconstructions like this. So what we have here is the aorta, the big tube that comes out of the pumping chamber of the heart that takes the blood all around the body, and it's got 2 blood vessels coming out either side of it, one on the left and one on the right. And those are our main coronary arteries. These are the most important blood vessels in the body, I think, because they supply the muscle of the heart. In this patient, we have some red stuff and we have some yellow stuff. And this is the atherosclerotic plaque. So this is the stuff that's building up in the wall of the blood vessel and causing some narrowing and potentially causing the patient some chest pain. We've got different types of atherosclerotic plaque here. The yellow stuff is your denser calcified plaque, your harder plaque, and the red stuff is the softer, non-calcified plaque. For me, when I started my research, all we could really do was say how narrow the blood vessel was. Anything else took too long to do. We couldn't even conceive that making images like this would be possible. But now, with the aid of the machine learning tools that help us draw many, many, many circles for every single patient, we can analyze these atherosclerotic plaques in more and more detail. Initially, we had to do this manually, and it took about an hour per patient. And when I've got a whole list of scans per day, there's no way I'm going to do this on every single patient. But now this takes only about a minute per patient. So it brings us into the realm of we could actually use this in clinical practice. And we could try and tailor our medicines and our therapies and our advice for patients in more personalized and detailed ways based on the heart disease that they have, rather than just a big, broad brushstroke aspect. So this is an example for me of doing something that we just wouldn't have had time to do before, but might have real use in clinical practice in the future. So this is one of the areas that's my biggest area of research at the moment, and one of the papers that will hopefully come out in January. So the third thing is doing new things that we couldn't do before. So everything I've talked about so far is technically possible, just took lots and lots of time. But there are some things that we can do with the machine learning and AI that we couldn't do before. In medical imaging, for me, this is something called radiomics. Now, when we look at a scan, whether it's an X-ray, an MRI scan, a PET scan, any of these types of scan, most of the time we're using information on what shape is there and how bright or how dark it is. But actually there's much more information in the image than just that. And what that's called is something called radiomics. And it's all about what the actual texture of the image is. How grainy is it? What pixels are next to each other? What range of pixel intensities is there in an area? All of this information can give us extra information about what is actually there. We can't take that information out as humans, but what the computers can do is do a lot of mathematical puzzles to take this extra information out. So this is a feature generative approach. We end up with enormous spreadsheets with huge numbers of numbers. And actually, this is helping tell us more things about the blood vessels of the heart than we could have done just with the human eye. So with these billion pixels, we're getting even more information out. The aim of all of this is to try and diagnose heart disease earlier and better. And we're learning a huge amount about what heart disease actually is, what is going on in those blood vessels around the heart that causes this plaque to build up, and why, for some patients, does it cause heart attacks, and other patients can have it for their entire life and never know. With all of those three things so far, the biggest problem is how we pull all this information together. So in clinical practice and in research, we've got a huge amount of information from what the patients tell us, to what the tests tell us, to what medications they've tried before, all sorts of information that we have to, as doctors, try and pull together and make a diagnosis and a management plan. And increasingly with the scans, there is huge amounts of information, and it can be very difficult to bring that all together to one single diagnosis. So there are other machine learning tools that can help us with that. The first is supervised machine learning that I've mentioned already, giving the machine learning models an answer, did the patient have a heart attack or not, and asking it to try and predict what risk factors are associated with that. So this supervised machine learning is helping us pull together lots of very complicated spreadsheets that were just a little bit too big and too complicated to analyze with traditional statistics. The second that I mentioned before is unsupervised machine learning. So for this research study, we had nearly 10,000 patients who had known heart disease. They had a diagnosis of coronary heart disease, and they'd all undergone an imaging test in Cedars-Sinai Medical Center in Los Angeles, where I worked for a while. They all had the same diagnosis, all 10,000 patients, but we wanted to know if there were different groups amongst those patients. Were they all exactly the same? Or were they a heterogeneous mixture of people who might benefit from slightly different treatments and have slightly different prognoses? So we put all of this information on 10,000 patients into the computer, and we left it for quite a few days. And at the end of all of this, the computer came back and said, yes, there are actually 3 different groups here. You think they're all the same, but based on these different factors, I can identify a green group, a yellow group, and a red group. And the most interesting thing is, those three groups had different prognoses. When we looked over 5 years of follow-up for the patients, the people in the red group were much more likely to come back to the hospital and have a heart attack, and the people in the green group were fine, even though they had the same diagnosis and were getting the same treatment. So this, for me, is very interesting because there's clearly something that we as doctors were missing. There's more information here, there's more diagnoses, and we can actually uncover these new patterns of disease with machine learning models. And I find that very exciting because potentially we can then find new treatments. The final thing that I think AI and machine learning can do for us is all the new cool stuff that's coming along. And that's a lot of what we've talked about already with large language models like ChatGPT and Claude and Copilot, and there's lots of different large language models. These models consume huge amounts of data and have a very broad training data set, and that gives you the possibility of asking it questions about a whole range of things. So I can ask it about some statistics code I'm trying to write, or I can ask it where I should go to in Utrecht when I'm on holiday there. I can ask it lots of different questions about a huge range of things, which means there are pros and cons to this that we'll come back to a bit later. But in medicine, what could the potential of this be? Well, these models contain some potentially useful information. They are great fun to try out. They can be totally wrong, so never believe it. Always look at a reputable source of information. But I do enjoy trying them out and just probing and seeing what it knows. Fortunately, ChatGPT still thinks that doctors are important. And when you ask it, how will artificial intelligence transform cardiovascular imaging, it comes up with some reasonably good answers. But it also says clinicians will continue to play a critical role. So I'm relieved about that at the moment. I also am very interested in the text-to-image generation models. So now within ChatGPT, you can get it to make images. Previously, they had a model called DALL-E, which you had to apply for, and I applied to use it early on as they were developing it. And I'm not very imaginative. I asked my husband, what should I ask it to try and draw for me? So we typed this in when I got access to it. I think this is pretty good. I think these unicorns all look like they're having fun as a steam train. These are all unique images generated by artificial intelligence, and actually they all look pretty real. We're going to come back to how that causes some challenges in due course. There is also latent medical information in these generally trained models. So if you ask this DALL-E model, which is now within ChatGPT, draw me a computed tomography scan of the heart with lots of colours, this comes up. This is quite a good representation of the heart. It's not perfect. Fascinatingly, machine learning models are not good at branches, and that goes fingers, really bad at fingers, bad at noses and eyes sometimes, terrible at branches of a tree. So if you ask it to draw a tree of winter branches, it just gets it wrong. Same issue in here. There are some blood vessels that are missing and not branching enough, and there's some blood vessels that are branching all over the place. So it's quite a beautiful image, and it has some potential here, but it's got a bit of a way to go. So that was in 2003. More recently, we made these images, again using a large language model, a slightly different one that we'd given some additional training on what MRIs and CT scans usually look like. So these are both MRI scans of a knee. Now, I don't spend a lot of time looking at knee MRIs anymore. I try and stick to the heart and chest, my favourite bits of the body. But I cannot tell you which one of these is generated by AI and which one is real. We made a survey for radiologists across the UK, and we had about 200 radiologists look at these images and a whole pile of other images that we made. Some were real and some weren't real. And actually, radiologists couldn't tell, in many cases, which was the real one and which wasn't. And there's good parts and bad parts to that. A good part is that we could use these types of synthetic images to test out medical tools. And because these are synthetic AI-generated images, they don't contain any information about the patient. These could be used in a very privacy-preserving way to test out a wide range of software tools that doctors and radiologists might want to use. There's also potential for doing what's called digital twin creation in medical imaging, where we can make pretend images that are based on a variety of patients and try out on those images different scenarios without impacting the patient at all. So there's lots of potential to how we could use these images also for training and teaching and other things as well. But, as many of you will be thinking, there's also the potential for using these for nefarious reasons. Medical fraud. As a journal editor, I have to be very aware that the fact that some of the images I might see in the journals are AI generated. I'm sure some of you saw pictures of the Pope in a bomber jacket in the past, the AI generated images, or even the video of the Queen on Channel 4, an AI generated video. So there is a possibility of using these for both good and bad things, and we really need to think about that. So there's potential for AI at every point in the patient pathway. I've talked a lot about that middle bit on this line, the analysing CT scans, taking images, analysing and getting reports out. But actually, the things that might make big differences early on, in the next few years at least, are at either side. Finding the right patients, helping people get to the hospital on time, organising appointments. These are actually much easier things for machine learning to do than analysing images. And that might make a bigger difference to us quicker and early on, whereas a lot of the things I've been showing you today might be 5 years or 2 to 5 years to actually get into clinical practice. So we mustn't forget about the efficiencies that we can make at the easier sides of the pathway, even though the stuff I'm talking about is some of the most exciting. Okay, so in the last 20 minutes or so, I'm going to talk a bit about the challenges of artificial intelligence in healthcare. As you've probably seen, I am very enthusiastic about all of this. I think it has huge potential to make my life better, to make everyone's life better. But there are also really important challenges that we need to think about and talk about and be very aware of as doctors, as patients, and as members of the public in general. First, I'd like to highlight some classic examples of bias in AI and machine learning models. These are classic textbook examples that anyone who studies artificial intelligence learns about, because they're really important ones. First of all, Amazon made a machine learning model that they had to pool because it was filtering their CVs, and it was filtering the CVs in a way that was biased against women compared to men. Microsoft made a chatbot, the Tay chatbot, which was on Twitter, and it was a wonderfully innocent chatbot that they wanted to learn from what was on Twitter, and within 24 hours it had to be pulled because the Twitter trolls had corrupted this poor innocent chatbot. I feel very sorry for Tay. Google misclassified humans as gorillas with their early photo algorithms. The Compass model in the US had double the false positive rate for recidivism for African Americans compared to Caucasians. And if you go onto ChatGPT today, there's still gender bias in natural language processing models. All of them have this challenge just of how language has been used in the past, and it's learned from the language that exists. So one of the classic ones is man is to computer as woman is to homemaker. These inherent biases with how language was used, because most language is the language of the past that it's absorbed, and things like the Gutenberg Bible and all of these just huge amounts of text on the internet, those gender biases in natural language processing models are very difficult to get rid of. So these are all textbook examples of machine learning, and one of the big reasons I show these firstly is for people to be aware, but secondly is to highlight these are all big multinational companies with enormous budgets for artificial intelligence and machine learning, hundreds of people working on this stuff, and these fairly major issues still happen. If you take a step back and think about who is making machine learning models in artificial intelligence in healthcare, a lot of it's being done by researchers such as myself. I have one postdoc. So the thought that biases and challenges with machine learning wouldn't come into health care issues is one that's just crazy, because if it happens to the big multinational companies, of course it's going to happen to other people who are doing these things. So as a researcher in artificial intelligence and machine learning, it's very important that I think about potential biases and potential challenges of what we're making at every stage of what we're doing. And I have to think about all of the sources of biases that are usual in healthcare, that we're always trying to improve. So things like based on age and gender, sex, ethnicity, education, access, rural versus urban. These are things that we're always thinking about when we're doing healthcare research. But we now have to think about additional things that are inherent to the machine learning tools that we're using. So we have to think about these up front, and then we have to try and test for them once we've made models. And it's very important that we do that. And this is an example, a great paper that did that with the machine learning model that they'd been developing. They were looking at how good was the machine learning model at diagnosing diseases on chest x-rays. And they found that it was pretty good. So their next paper was looking at, are there any sources of biases in this model? And they found that actually, yes, there were. It underperformed based on sex, based on age, based on ethnicity, and also based on payment type. So this is a US study, so payment type is a surrogate marker of socioeconomic status. So all of these things were additional biases in this model. So their third paper, they improved the training of this model to try and fix these issues. So we need to identify it, we need to be aware of the issue, might happen, we need to try and identify it, and then we need to try and fix it and improve it. And this is a constant cycle. So AI and machine learning models, we're always improving them and updating them to try and address these and many other challenges. There's also an issue of trust. Do we trust the AI machine learning model? Or do we not trust it? Trust is a sliding scale. There are some machine learning models I'll trust no problem if it's organizing the best time for my students to make an appointment with me. I'm going to let it just carry on. If it's diagnosing things on a scan, I want a human to double check it. So we've got variations in how much trust and autonomy we want to give these machine learning models. And it does vary very much based on how important that task or decision is. We also have to think about data security. It's really important that all of our patient data is kept held very securely on on the computers that we use. There's a lot of work that goes into cybersecurity to maintain hospital and research computers to the most secure level possible. Privacy is obviously very important. We spend a lot of time making sure anything that we're using is anonymous and can't be identified back to individual patients. So we've got lots of really important things in this area to do. When it comes to machine learning models, we also have to think about how we understand what they're doing. So as a doctor, I'm most interested in machine learning models where I can learn something new and I want it to show me it's working. A lot of early machine learning models, just because of computational power issues, were black boxes where we just didn't know what they were doing. It was all hidden under the hood. But in healthcare, increasingly, we're using something called explainable machine learning or explainable AI, where we actually delve under the hood of the machine learning models in lots of different ways to try and work out what they're doing. Because for me, that might help us understand disease better or find new patterns in the disease. So I really want to learn from the machine learning models rather than just being told what the answer is. And then I said I'd come back to this, challenges of large language models. There are many. And they can be, I think I've said this a few times already, they can be really convincing, but absolutely, totally wrong. And And there's challenges of what you believe and what you do and don't use based on what they come up with. There's also issues of plagiarism and copying and appropriation, or even stealing from people, particularly when it comes to authors and artists. What is and isn't within these machine learning models is difficult to know sometimes. And this is a really important issue. Everyone should be paid for the resources they create in a fair and equitable manner. There's also issues of what goes into the training. We don't know as individuals when we're using ChatGPT or Claude or any of these other models or Copilot what was in the training data set. When I use artificial intelligence and machine learning models in healthcare, I know what is in the training data set. That information is available in papers about the training of these models. So I struggle with the not knowing of the large language model, because if it was trained on rubbish, it's going to give me rubbish back. So that aspect of what's in the data set and trust and accountability and biases is a big problem. There's also the one we've mentioned already, that deep fake and fraud and cheating. And as a journal editor for medical journals, I have to be very aware of people creating text and people creating images that are copied or fake. I was sent an article to review recently. We do peer review where articles are sent out to experts in the field and we read them. And I read through it. This is really good paper. I would write something like this. And then I realized what they'd done is they just put every paragraph through ChatGPT. And it was my paper, because it was my paper, but they just paraphrased it. And that's not allowed. A big question is, do you think you can tell whether an image is generated by AI and machine learning or not? This is a beautiful picture of a heart, but no heart has that many blood vessels coming out of it. So this is AI generated. And when you ask people on Twitter, do you think you can tell? A lot of people now say no. So nearly 3/4 of people don't think they can tell. And I increasingly am struggling with images. With text, I can still often tell in my field, but not with my area of expertise. Images, I think there's some very impressive images out there that I can't tell anymore. But this is a really interesting one that's constantly changing as well. We also have to think about what patients think, and I'm sure everyone in the room has thoughts and ideas on this topic. It's one that's a really popular one to talk about at the moment. And this was a Pew Research poll published in Forbes, so we don't know exactly who was in this set of patients. Classic methodology, not published, but 60% of these patients did wonder that would their healthcare practitioner rely too much on AI, and would it lose that personal connection to a doctor. There's people that love chatting to a chatbot on a phone rather than having to pick up the phone and speak to people. There's other people who absolutely hate it and just want to speak to a real person. I'm in that, even though I'm an AI developer, I just want to speak to a real person on the phone. There's also ethical issues. So these are our classic pillars of medical ethics: autonomy, beneficence, non-maleficence, and justice. They've been the same since the time of Aristotle and Plato. But we now have some more to worry about. So artificial intelligence and machine learning have given us a whole pile of new things that we need to think about when we're thinking about medical ethics in particular, but actually the ethics of using these things in general. And there is potential to cause harm. This is a fantastic paper that was published in the British Medical Journal just last year. And they looked at a variety of large language models, ChatGPT and other ones that were available online. And they tried to make them generate health disinformation. And they asked, well, could these models generate health disinformation? And unfortunately, the answer was yes. They then asked, well, these companies have safeguards in place to try and prevent this, so can we trick those? And the answer, unfortunately, is yes. And then they thought, well, if we report this to the companies and try and help them improve their models, does this help? And the answer is yes. But even with that, Up to 40 blogs could be generated in 40 minutes containing medical disinformation. So that's a blog article every minute that could be being generated out there with information about health that's totally incorrect. So this is why I tell people, be very careful about the internet when it comes to health information. Go to reputable sources, the British Heart Foundation, the NHS web pages. You just can't believe what's written on the internet anymore, because this is being created in huge volumes. An important one when I talk to people around the world is who pays for all of this. Is it the doctor? Is it the patient? Is it the insurer? Is it the manufacturer? Within the NHS, NHS Scotland, NHS England, we've got issues of how do we get this into clinical practice. There are upfront expensive costs. A lot of the things that are developed for heart disease are being sold in the US per patient £3,000 a time. A scan of the heart in Scotland costs £250. So we're not going to pay £3,000 just for a little bit of extra information based on an AI and machine learning tools. So there is a challenge here of how we get this stuff, get the stuff that works into the hands of patients, and balance out that cost challenge. And it is a big challenge around the world, because we're in a very fortunate position. We have access to state-of-the-art scans, lots of ability to have all these tests. We've got some developing AI machine learning tools that are being used in clinical practice in our NHS. I was in Tanzania last summer. They don't even have a working computer in one of the hospitals I was in. So we're talking about huge disparities in what people can and can't access around the world. I also spend a lot of time thinking about how we're going to do this in the right way. I work with various societies and organizations and companies talking about how we regulate and monitor artificial intelligence. We've now got an Artificial Intelligence Act in the EU that has a sort of triangular structure to how things are regulated. There are some things that are minimal risk and you can kind of get on with doing them, but there are other things that are high risk, like diagnosis on an X-ray, and these need much more in the way of regulation and monitoring than other things. And the circular picture here on the right is part of graphics we put together for the British Standard Institute's framework for artificial intelligence and machine learning in healthcare, which kind of highlighted that this is a cyclical thing. It's not just a make machine learning model, use machine learning model. We have to think about how we develop it in the right way to make the best use of it for patients. And we also have to keep an eye on it. We need to monitor it and check that it's doing what we think it should be doing when we actually deploy it in hospitals. So we have a cyclical model of AI development that involves checks at each of these stages, so that if we're using something in healthcare, we can be confident that we're using it in a safe and ethical way, rather than just letting people go at it. So I spend a lot of time thinking about how we do this in Scotland. It's not easy, but I do have hope for the future. So finally, a few images. We do have to remember that machine learning AI doesn't always get things right. This is a CT scan of the heart. It's got some drawing around it that it highlights different blood vessels, and I fed it into one of our machine learning models. It is a beautiful fish, but that wasn't what I was going for. And this is another one that I really love. This is a CT scan of the chest. I fed it into Google's Vision AI, a multi-purpose machine learning model. It is 58% sure that it's the Tottenham Hotspur. So my biggest thought on this is humans are essential. We are not going away anytime soon. Many of the things in healthcare that I do are useful things for augmenting what we do. They're not going to replace what we do, and we need to keep an eye on them. So humans in the loop is very much the way I see artificial intelligence and machine learning. And I think it's very important to remember that it's only learning from what we did previously. Humans still have the innovation, and the imaginative aspect that the machine learning models are not intelligent. So we are still doing the most exciting things rather than the computers. So with that, I'd like to finish. I'd like to thank the British Heart Foundation again, and anyone who supports British Heart Foundation, because all of the stuff I've talked about has been made possible by them. And I think a picture really does speak 1,000 words, but maybe artificial intelligence and machine learning will help it speak even more. Thank you very much.
Does anybody have any questions? Yes.
Yeah, you talk about the training that goes into these. There is, and I'm not going to mention the name of a particular man called Kennedy, who is, there's an enormous amount of conspiracy theories in health. If that gets into the training of these models, what's that going to cause?
Yeah, it's a very good point, and it comes back to that. If we've got a large language model, it has absorbed the internet,
Yeah.
including all of this stuff, and therefore what comes out, if it's being regulated in any way by the companies to say, well, we can't say that, we need to say these things, that might, in those circumstances, we might not see those styles of different information emerging. But if there aren't, we will just see disinformation, and that's where those blogs, one every minute could be generated. That's where the information comes from. So that's why we have to be very careful of generally trained models where we don't really know what went into them.
Yes.
One of your early graphics was where you showed three, when the large language model went, analysed what you'd had there before, and it found a spidergram and etc., etc. And what you said was, of those three different diagrams, the outcomes for each of those groups of patients was different. How do you reverse that? Up until now, you would have been treating them all the same. How do you reverse things so that, because health should be about prevention, not actually about cure in that sense, so you would have to treat those people differently. How do you then say what's exactly going on that led to them ending up with three different sets of outcomes, and how do you then put that into general practice in the health economy?
Yeah, exactly. There's no point knowing that something is different without actually trying to understand why and actually improving it. So with those three groups, we know that there's one group that's much higher risk. So we can take that group of people and we can try to give them the new treatment, latest drug that's come along, a different exercise program, a whole package of blood pressure, anti-smoking, lifestyle modifications, and try and treat them much more aggressively to try and then reduce the number of heart attacks in the future. So we use these sort of machine learning tools to stratify patients, and then what we do is a randomized control trial of new treatment or not new treatment in the high-risk patients to see if we can get the high-risk patients having outcomes as low as the low-risk patients. And part of that involves there being new treatments for the disease, and with the machine learning models we can identify which aspects are the things that are most driving the outcomes. Is it blood pressure or is it cholesterol? And work with drug companies to try and develop new treatments in those areas. So these are all new ways of testing out, did a drug work or did a change in management work? But yeah, it's really important. We can't just look at new patterns and do nothing about it. We have to try and identify those people and then organise the randomised controlled trials to try and improve those things.
Just to follow that up,
Yeah.
I was thinking particularly in the group that has the best outcome, one of the things that we seem to be saying is the people all presented, and my view is, well, how do you get to the people before they've even got to the disease? Because what is in their profile that actually says within the population we can identify that Joe Blogs, Mrs. Blogs and baby Blogs will all have this problem?
Yeah, prevention is so important because 1 in 3 of us will die of heart disease, and most of us will never know that we had heart disease. And the thing that we do at the moment to try and work it out is to do risk scores. So we take your age, your sex, whether you smoke, whether you have diabetes, we check your cholesterol, your blood pressure, and we put this all into something called the ASSIGN score, which is a cardiovascular risk score tailored for the Scottish population. And there's a project ongoing at the moment that's trying to update that and make that more accurate. So if you get a letter from your GP, you could help the researchers in Edinburgh and Glasgow and Dundee to actually make this more accurate. But that's only so accurate because that's only taking the peripheral stuff. So the question I have is, can we look at the heart itself and take people who have no symptoms, but maybe some risk factors for heart disease, maybe they have high cholesterol or high blood pressure or family history, and look at their hearts and go, well, your heart's normal, great, don't start smoking. Your heart's very abnormal, let's give you some medication and try and prevent you from having a heart attack. And that's what we've been doing at the moment in what's called the Scot Heart 2 study. So we've taken 6,000 patients from all across Scotland, and half have had a CT scan to guide their treatment. And it ranges from being told your heart's normal all the way through to people who've had bypass graft surgery and stents put in, and half have just had the risk score. So we're scanning our last handful of patients, and in 2 years' time, we should be able to work out, has that helped? Does it reduce the number of admissions to hospital, the number of heart attacks, the number of strokes? And we're going to look at all of these things, and I would love it if we could prevent more heart attacks. But yeah, 2 years' time, I'll come back.
Okay, just have a very quick one on that. To add to that, because I'd like to be in the green, not the yellow or the red.
Yeah.
And I would like to have known that 30 years ago.
Yeah.
And that's in the sense the question. And I suppose you've answered that we don't know yet. But could AI help with that?
Oh yes, definitely. Because we've recruited 6,000 patients and scanned 3,000 people. I've looked at 3,000 CT coronary angiograms. It's a lot of hearts and blood vessels, and definitely the AI and machine learning, if we're going to do this on a national basis, I've done all of this in Edinburgh, but if we're going to do this on a national basis, we need tens of thousands of scans to be done. So we're going to have to train more machine learning models to do what I've been doing, which is why every time I draw a circle, it's saved, so we can train more machine learning models.
Yeah. I know I'm not in the green. Yes, at the back there.
So, when you look at large language models, you were talking about like the ones which are released to the public. They're tokenized. They take data and they tokenize it. Is all I know about it. But surely, when you're looking at is this the case? When you look at CT scans, for instance, you're actually making a specific large language model by tokenizing that scan data. Is that something? Is that the right? Is that a realistic approach?
So what we do with images, whether it's a CT scan or a photo, is we do something called a convolutional neural network, deep learning, where we take a sort of square of data and summarize across the scan. So it's like tokenization, but in a graphical format. So convolution is a way of bringing down the data to the key parts. So instead of having a huge matrix of pixels, you have smaller and smaller and smaller matrices of pixels with what's hopefully the key information. And you do that again and again and again and again and again, and the machine learning model runs on the computer for over the weekend while it does this convolutions across every single image on the entire CT scan. And then that summarized information then gets interrogated back up to what is the diagnosis or not. So tokenization, but in a slightly different way for images. That's one approach, which is proving the most useful approach in images at the moment, across the board for most medical images. But there are actually other approaches as well. So graph-based, point-based, lots of different maths underlying based. So there's lots of potential approaches, but convolutional neural networks is the one for images at the moment.
Thanks. Sorry, don't catch your eye at the back there. Yeah, yes, yourself.
Just to ask, does an institution like the NHS have its own data centres for all the information that it's obviously mining through and the information that will be added to it? Or does it use third-party data centres?
So in Scotland, we have all of the data held by Public Health Scotland, and it's all held on the National Safe Haven, so a secure, trusted research environment where all of that data is. That data is, you have to do a lot of things to get access to that data. You have to be certain people with a project, it has to be ethically approved. There's a lot of things that are checked to be able to access that data. So not everyone can access that data, and you can only access the very small amount of data that you need for the specific research question that you have. We also can't really do machine learning in that yet, because one of the very important parts is you need to be able to take the results of the research out. So training a machine learning model would mean taking that information out. And we don't yet know how to do that in a way that's really private and secure. So at the moment we can use it to test machine learning models, but that's all. So other data sets are usually used for research that are held within universities or NHS trusts rather than on a full national basis. And this is data that's being collected in the form of consented research studies. So research participants agree to their data being used for certain things. So there's different things that we can and can't do in different data sets. And that gives you a bit of an idea of the scope and scale of what's in different places.
Thank you. I tried to get around everybody without going down. Yes.
The bias in the data sets, is it better or worse than the bias in the general population or the medical population?
Yeah, one of the things that I worry is that the stuff that gets put into machine learning models is often the good quality data. So the usual data has things missing. There's never a complete data set. Everything normally has something missing from it. And maybe some of the image quality is great, but some of the image quality is poor, and there's things that are missing here, there, and everywhere. When it comes to the training of machine learning models, they rarely train models on the messy data. It's usually trained on the good stuff, which is why when we take models into clinical practice to actually use, they never seem to perform quite as well. So that's why we're really trying to encourage companies and people developing models at the moment to train on the messy stuff, because that's what they're going to use. So at the moment, the biases are much lower. The variation is much less than what they're training on, which means that the biases are much bigger. So we've got definitely some areas of work to do there.
Interesting. Yes, I've got a couple down. Yes, sir, and then I'll come back to you. Yes, yes.
You mentioned that you were a journal editor. How many of the papers that you receive have been generated by paper mills? How do you spot them? Is it a human that spots them, or is it a machine that spots them?
We do now have machine learning models that try and spot these paper mill produced articles. They're not very good, actually. They spot a few of them, but actually the biggest thing we rely on is that peer review process, where experts in the field read the papers and then write and say, there's something dodgy about this. So we use both, but at the moment the humans are better than the machine learning for spotting those things.
Do any get through?
So I am editor for some quite high tier journals. So I would say not at that level. So if you're talking about the FJ, Lancet, New England Journal, Radiology, these are quite high level journals. It's very difficult to get into those journals anyway. 5% acceptance rate sort of thing. So that we've not seen one yet. At the lower end, where journals accept everything, there must be.
Try marking 2,000 word student scripts, 50 of them. Sorry, yes.
Are there big companies getting involved in building these systems? And if so, are you worried that they will build in bias to maximise their profits and minimise the risk of them being sued?
Yeah, there are definitely big companies. In a couple of weeks' time, I'll go to RSNA in Chicago, which is the biggest radiological conference every year. And every year, the floor space of the exhibition hall that deals with AI tools expands. And it's probably, last year, it was the size of 3 rugby pitches. And I'm sure it'll be bigger again. So there's companies of all sizes involved in this. So the second question is a harder one. I think the regulation aspect of AI in healthcare is really important. And on a EU level and on a UK level, I think we've done some really good things to try and make sure that the things that we use are the things that actually benefit patients and the health system, and we don't let in things that don't. Sometimes I wonder if we've been a little bit too strict, but that's another problem. In the US, anything goes. And I do worry that there are things that people can buy, either doctors or patients, that have no benefit at all. So I think it's a very place-dependent thing. We're currently okay here, but I wouldn't want to be working in the US.
I'll just get a couple of the top. Yes, sir, right up the top. You. Yeah.
So, could you explain what kind of information that machine learning can get from some pixels? I think maybe some obvious ones would be color, brightness, but I think you also mentioned in your presentation that it can determine textures just from pixels. Can you maybe talk about the textures and then maybe other information machine learning get just from pixels?
Yeah, this is a really interesting area, and it actually emerged during the war when they were looking in World War II on photographs for missile silos. So they were looking for certain shapes and certain clusters of pixels, and they had hundreds and hundreds of photos, and they tried to develop better ways of doing it. So you mentioned some of the things already, how bright the pixels are, what shape the pixels are, but we can actually look at orders of magnitude away from the pixel. So does this pixel have a similar pixel next to it, and what's next to it, and what's next to it, and what's next to it? So these different orders of magnitude away from the pixel in 3 dimensions builds up information about what that pixel might be. So something that's very solid will have a dark pixel, a dark pixel, a dark pixel, a dark pixel, whereas something that's a bit more like a honeycomb might have dark, bright, dark, bright, dark, bright. So that hopefully gives you an idea of some of the complexity that we can take out. And it goes from brightness and size and shape all the way to multi-levels of complexity, depending on how long you leave the computer running.
I'm aware that we need to get Professor Williams to a train by 9:20, but I'll take a couple of more questions if I may. Yes, sir.
I was just wondering, recently I've just been learning to download small LLMs onto my own computer, and I was wondering if when you're doing your research, do you download these certain models into the safe haven?
So we don't do it into the safe haven, but what I do is download them onto our university computers, and rather than using real patient data, we have synthetic data. So it's like real data, but it's not real data, so that I know that I'm using something that's privacy preserving. And we can use that to try and train these models and then see what they come up with. What I'm particularly interested in is, can it help me write reports for scans just a bit more quicker and more efficiently? And can it help me summarise those in a way that patients can understand more easily? My reports contain lots of technical information for the hospital doctors, for the GPs, but could we automate the making of something nice and simple to explain the key results as well? So it's great fun to do, and yes, we are doing it, but we won't be doing that in the National Safe Haven for a long time. Many technical and cybersecurity things to think about first.
Maybe one more. Did you have your hands up? Yeah.
Yeah, in the context of your own research, cardiovascular disease AI research, I'm thinking about data fusion. Does it make sense to think about fusion of images, acoustics, temperature maps, pressure maps, biosensor data? Does that make sense, or does it not make sense and only make sense in the context of digital twin manufacture of what?
Yeah, I love bringing everything together, and all of the information tells us slightly different things about the patient, and only with all of the information do we really get a proper picture of the whole patient. So I think definitely yes. There's another aspect as well, which is bringing extra information out of the images in terms of pressure and wall shear stress, which we can actually generate from computational models, just like aircraft and racing car design. We can do that in the blood vessels of the heart, which is really cool.
I think we could be here a lot longer.
We could.
You've been away going home at 1 o'clock. Michelle, thanks very much. I'm going to ask David Waller if he would give us a little vote of thanks.
Well, if truth in hearts that perish could move the powers on high, I think the love I bear you would make you want to die. This long and sure set liking, this boundless will to please. Oh, you could live forever if there were help in these. Houseman was arguably the least cheerful poet ever to write in the English language. But in his own way, he may have been quite unintentionally prophetic. And this evening, I think we have had quite a remarkable insight into the process of extracting truth from parts that really are perishing. And perhaps not making us live forever, but giving us a few more years at least. And so I think we've had a remarkable insight into an area that certainly stretched our minds as well as our hearts. And so I'd like us to thank Professor Williams for giving us such a fascinating tour around such a relevant and really quite remarkable subject. Thank you.